The linear variational method is one where you write your trial function as a linear combination of other functions. I know, preferably an orthonormal set if you can find one, but a linear combination of functions that obey the same boundary conditions of the wave function. So these f's, okay, you'll notice your coefficients are linear here. Okay, so all the parameters are linear, and if you did that, okay, and you can write your guessed energy as a function of these coefficients, C1, C2, C3. So it's just a matter of finding the best values for these C3s to get your lowest possible energies. These functions you have here, F1, F2, F3, and so on, that's what you would call your basis set, okay, or your basis functions. Okay, and so that's a common strategy that's used for approximation. You look at, usually you have a system that you cannot solve exactly, right? But it might be similar to a system for which you know the exact solution. You can use the wave functions for that simple system as your basis set, provided you're looking at the same boundary conditions. So for example, let's say you have your, instead of a particle in a box, let's say you have, instead of the potential energy being 0 everywhere, it's equal to V naught from, let's say, from L over 4 to L over, let's see, from 0.4 L maybe to 0.6 L. Okay, so it's V equals 0 at x less than 0.4 L and V equals 0 at x greater than 0.6 L. But it's equal to V naught from 0.4 L to 0.6 L. Okay? So your wave functions here are still going to go to 0 at x equals 0 and x equals infinity and x equals L, right? So you can use your psi square root of 2 over L sine n pi x over L, where n equals 1, 2, 3, okay, as your basis set. Okay, so you can. So this is not going to be your psi in this case, but you can use that as your basis set, f sub n. Okay? These are not going to be your wave functions, but you can write your wave function as phi would be equal to C1 F1 plus C2 F2 plus C3 F3 and so on and so forth. Okay? To get the correct wave functions for this problem, because this problem you're going to have a hard time finding the exact closed form solution for your wave function. So you write it as a linear combination of the particle in the box functions. Okay, and the nice thing about this is if you try to do that, you can set up the solution to this problem using what's called a secular determinant. Okay. And the solutions will give you, okay, depending on the number of basis functions you have. If you have n basis functions, you'll be able to estimate not just the lowest energy, but you get an estimate for the n lowest energies. So if you use 3 basis functions, you get an estimate, upper limit for E1, E1, E2, and E3. Okay? And so this is the secular determinant that you would have to solve. And you're just going to have to wait till graduate school to get into the details for that one, how to set that, how to derive that. Okay, but the idea here is this Hij is this integral right here. Hij. All right. So F1 H hat Fj. And Sij is F1 Fj. So if you have a, let's just say you use 2 basis functions, F1 and F2. Okay. So what is H11? It's gonna be F1 h hat f2, f1. Okay, so that's going to be the integral of f1 star h hat f1 d tau. What is h12 going to be equal to? h12 is going to be f1 h hat f2. Okay, and so your secular determinant is going to come up like this. You have h11 minus ws11, h12 minus ws12, h21 minus ws21, and h22 minus ws22 must be equal to 0. Okay? And what happens, how do you expand a 2 by 2 determinant? Do you remember? A, B, C, D is equal to AD minus BC. So this times this minus this times that is equal to 0. You'll get a quadratic equation, right? You're going to have a W squared term. And so when you find the root of that quadratic equation, the root, you'll see two roots, two possible values of W's. So the lower one would be an upper estimate for W1, the lowest energy. The second W value would be the upper estimate for the second allowed energy level. Okay? So if you have n basis functions, then you get n possible values of W. Right here we have two basis functions. We get two possible values for W. That would satisfy the requirement that this secular determinant be equal to 0. So you can get estimates for the n lowest energy levels. And then what you do is for each of those W's, you can plug it back in and solve for the coefficients for the eigenvector, what's called the eigenvector. So for your phi 1, which is going to be C1 F1 plus C2 F2 plus so on. So you get a set of coefficients for each one of those. Oops, it's time to go. All right. So that's what you do with the particle. Oh, here's an example right here. We'll talk about that next time.